Here we are in section 3.2. This is the lecture for 2/22/21. Lots of twos. February 22, the Monday, lecture time, and we've got sections 3.2 and a little bit of 3.3 probably up for you here. 3.2 is a longer section. My plan is to have the test go through 3.3. If I don't happen to finish it, I just won't put any problems at the end of 3.3, but we'll see. I would like to get a dozen sections in, and even that doesn't get me to chapter 9, but that's the way it is. 9 is so much like 8, it'd be nice to take advantage of the duplication there, but we'll just see how it goes. Meanwhile, let's kind of get through some of this stuff. I'm not covering everything, I'm just covering the less complicated examples, which is most of them, I believe, and the occasional homework problem as time allows. So anyway, we have probabilities that they talk about for the discrete random variables, and we could have probability distribution of x, and we could have probability of the x value 0 being just p of capital X equaling 0. That's pretty straightforward, but there's a shorthand that can be used. If I can just get the screen to maximize, it doesn't want to. Have little p parentheses 0 is a lot better notation. So that's frequently used versus the more tedious notation of capital P of capital X equaling 0, just little p of 0, little p of 1. No, those are perfectly okay. We have a Cal Poly Department of Statistics. Now, I went to Cal Poly. I graduated Cal Poly Pomona. They only had a math department at the time. I haven't checked into it. Maybe they've got a stats department now. Maybe it's the San Luis Obispo, their sister school, but who knows. They have a lab with 6 computers reserved for stats majors, and X is the number of these computers that are in use at a particular time of day. So they pick, say, noon or whatever time they pick, and suppose probability distribution of X is in the following table. So all this is the number of computers that are in use, anywhere between 0 and 6, along with the probabilities of each of these occurrences, all 7 of them. The most likely is 3, 25% is the maximal probability. And it tapers off towards 0, not likely, and even 6 isn't all that likely, so the whole thing adds up to 1, obviously. But you can use elementary properties to calculate other properties of interest. So if you needed to know about the probability that at most, maximum, 2 computers are in use, you could say, for example, X is less than or equal to 2. 2 is the most it could be. In other words, X could either equal 0 or 1 or 2, and just simply add them up. Very simple stuff here. And so we just add them up. 0.05 for the 0 use, no computers being used, the 10% for 1 computer being used, 15% for 2, total of 30 to answer the question. And now if they're interested in at least 3 is a minimum, computers in use, you could say 3, 4, 5, or 6 if you want, but we could also notice as a complement of the prior event. If the first one had 0, 1, or 2, and we're interested in 3, 4, 5, and 6, why not just take what we have and subtract it from 1? A little bit faster, especially if we had a much longer list. But you could add them up if you prefer. Same idea. What if we ask between 2 and 5 computers inclusive are in use, which includes the 2 and the 5, of course. And so we add up all 4 of those probabilities to find a 75% chance of that event occurring. Now, if it's strictly between 2 and 5, this book makes a big deal out of this. Other books don't so much, but if it does not include the 2 and the 5, notice how we do not have the equal signs anymore. It's between 2 and 5, so 2 is not included, 5 is not included. It's just 3 and 4 that are available. Now we're down to only a 45% chance. They're still the 2 most popular ones, but it's a lot less than the 75% from before. The probability distribution, sometimes known as the probability mass function, of a discrete random variable, RV, is defined for every number x by p of x, which is the probability the random variable is equal to a particular value of x. And they get into some math notation here with the function situation notation that we used before. But we do have to have the sum of all the probabilities equal to 1, no matter how you slice it. Every probability has to be greater than or equal to 0, and certainly the sum has to equal 1. Now, that's fundamental for probability. So we have the previous example is simply given in the problem description. Sometimes it's given by a table. Those are some of the easier ones to do. And we could look at several examples now. So this is an example-filled lesson here, lots of them. I'm not going to cover them all. So if we have 6 boxes of components that are ready to be shipped by a certain supplier, the number of defective components in each box is as follows. So some of the boxes have no defects. Box number 1, number 3, number 6, no defects at all. But then on the other hand, box 2 and 5 have 2 defects apiece. One of these boxes is randomly selected for shipment to a particular customer, and X is the number of defectives in the selected box. There are 3 possible defective numbers. The X's are in blue, 0, 1, or 2. And of the 6 equally likely simple events, like rolling a die, single die, 6-sided, and you'd have equal chance of any of these, you'd have, as we pointed out, 3 of the boxes have no defects at all. 1 of them has 1 defect, and 2 of them have 2 defects. So we could just look at the probabilities. For no defects, we have 3 chances out of 6, 3 boxes out of 6 fit the bill for that. That's exactly 50%, half. 1 out of 6 is box 4, that's around 17%. And then to have 2 defects, 2 boxes are fitting the bill on that one, about 33%, 2 chances out of 6. So we have the various probabilities that go with the various values of the number of defects. And so yeah, it completely specifies the function. And if it happened over and over again, assuming this is a representative sample, there's not much here in the sample, but assuming that's representative, which it probably is, we could say in the long run that no defects would happen about half the time. And 1 defect 1/6 of the time, and 2 1/3 of the time. So let's move on to the next one. Looks like a Bernoulli function, and so we consider whether the next person buying a computer at a certain store buys either a laptop or a desktop model. And we could say X equals 1 if they buy a desktop and 0 if they get a laptop. So 20% of all purchases happen to be a desktop during a certain week. So we could say that 20% get that X equals 1, i.e. a desktop. So they want a desktop 20%. There it is, 0.2. Then by default, the laptop, 1 minus 0.2 is of course 0.8, 80% chance that a laptop is purchased. However, this book does like to throw in the extra that if X happens to be any other number besides 0 or 1, there's no chance of it occurring. Well, many books don't even specify that, but your book is quite specific on things. We're a mathematically heavy book, and that's fine. So we have no chance of X equaling something besides a 0 or 1. This is meant to be another example of the Bernoulli function. We have a line graph, not commonly used, but they are used, and kind of like a thin histogram or bar chart, I guess. And so X could either be 0 or 1. There's not much going on here. 0 has an 80% chance. Notice that's 0.8 relative to 1. And here we have a 20% chance. They didn't put any other tick marks here, I notice. But 20% chance of being a 1, that is a desktop. 80% chance of being a 0, that is a laptop. Another example, lots of them today. In a group of 5 potential blood donors, and they're labeled A through E, only A and B have type O positive blood, so we already know who they are. 5 blood samples, 1 from each individual, will be typed in random order until an O positive individual is found. Let the RVY be the number of typings necessary to identify an O positive individual. So we have to get an individual one. So the probability of 1, little p of 1, is on the first try, A or B is typed first. That's the easiest one. And yes, you have 2 chances out of 5 for that first draw to give us what we're looking for. That's 0.4, 40%. What about on the second draw? Well, in other words, we have to get a non-O positive first. That's C, D, or E. They're the ones that did not have O positive. So we continue to go to a second draw, second type, and then we get A or B. So then we have to invoke conditional probability, which looks harder than it is. You have to get the failure first and then the success, given that the failure happened first. That does change the probability. So let's take a look at getting C, D, or E first. That is 3/5. Just trying to circle it there. That's a kind of a chance of a failure. It's C or D or E, 3 out of 5. But now notice what happens on the second draw. To get the success, we know there are 2 successes, so the 2 is just where it's supposed to be. But now we only have 4 people left, that's where the conditional kicks in. This says we've taken one person out of the mix. There's only 4 left. 2 out of 4 is that probability. Of course, that's 50% by itself, but we're more interested in the total, which does work out to be 30%, 0.3. We just continue with this every step of the way. And on the third draw, you'd have to have C, D, or E done first and second, and then comes A or B. So let's take a look at the first ones. On the first draw, it's exactly the same as before, 3 chances out of 5 to be a failure, so to speak. We didn't get our O positive. And then we have taken one of the failures out, so 3 minus 1 is 2. And we've taken one of the people out, so 5 minus 1 is 4. So we have 2 out of 4 left just by crossing off either C, D, or E and just looking at the remaining 4. But then we shift gears and go to the success, and we still know there are 2 successes to start, 2 out of originally 5, but now we only have 3 people left because we've removed the first 2 people. So this jumps up to 2/3 now. When you run through all of this, cancel all the little fractions and everything, you will get 0.2, 20%. And then finally, to get to the fourth one, you'd have to have C, D, and E all done first. And so basically that's all you have to look at. Let's take another look. Start off exactly the same as the last 2 examples. And then we continue with the second draw just like the prior example, 2 out of 4 failures. And then finally at the third one, we have only 1 left out of the 3 that are left. So we've taken 2 away, down to only 3 people left, and only 1 failure is left. And then what happens is you have 2 out of 2. They did not put that in. They figured it was obvious. But to look at that finally getting a success on that 4th try, all you get is a success because that's all you have left is A or B. And then it's 100%, so you don't have to multiply by 1. But this does work out to be 10%. And they'll show you a table coming up. But we should also mention that P of Y will be impossible if Y is not equal to the 4 values. You can't have a 5th value or a 6.2 value. It isn't going to work that way, or a negative value. None of those make any sense, so they add in that little extra to make sure you get that. Here's our table where on the first draw, Y is equal to 1, 40% chance. It keeps decreasing very regularly. This is amazingly regular. Second draw, 30%, then 20%, then 10%, sorry. Okay, so we have a line graph, and you can see how regular it is. It's kind of like linear. Straight line. Well, that's coincidence, of course, but we do have a line graph of the PMF, the function there, probability mass function. And they talk about physics a little bit. You can take a look at that. More commonly used, though, is the probability histogram. And perhaps you've seen these to relate to what we just did. The histogram is just a special kind of a bar chart where they all basically touch each other. They're all touching. They're not with gaps. A regular bar graph has gaps and usually explanatory verbiage that sometimes takes up a lot of room, so they have to allow that extra room for the categorical data, such as how do you get to school? Do you walk, do you take the bus, do you drive a car, whatever. Those don't have numbers on them, but here the numbers kind of force a better mathematically looking histogram, numerical sense. So the process is to squeeze them together, unless of course you have a blank cell and nothing's in the 4 category, maybe you have something in the 5 category or something, then you would have a natural gap. That's okay. And this is also an example from before where we had 80% in the 0 category, 20% in the 1 category. Notice they've not put a scale on the y-axis. I find that to be a bit peculiar. But this is more of a bar chart. Most books distinguish between the two. Your book doesn't seem to do that too much. They're just calling them histograms. Okay, whatever. It's often helpful to think as the PMF as being specifying a mathematical model for a discrete population. So now we look at a household in the critical region at random and let X be the number of individuals in the selected household. It just won't expand. I don't know why it won't expand. But anyway, hope you can read this. I've made the page about as large as I can. See if I can, well, I can't seem to make it grow any further. So anyway, that's as far as it'll go. Anyway, number of people in each household. Here would be 14% chance of finding a household, only one person lives there, person living alone. Or to get to 10, now you have 1 chance in 1,000, according to a certain region. This may not be universal from every region, or may not be across the country. It may just be a particular zone, which is unspecified. And of course, if you had 11 or more, which is certainly possible, those numbers apparently are below 0 to 3 decimal places, so they are then effectively ignored because they're just that rare, at least to 3 decimal places. Also, 4 seems to be the most common one. At least on this survey, 26% of the households have 4 people in them. And they do say this is close to the household size distribution for rural Thailand. How about that? And, by the way, the probability of containment for multi-type branching process models for emerging epidemics done way back in 2011. Back in 2011, 10 years ago, they were looking at this kind of thing. And so I guess the more people per household, the more it's likely to spread. So there you go. And this may be based on 1 million households for a very large region. And one way to view the situation is to think of the population as having 1 million households, each with its own x value, and the proportion for which is given by P of x. Or you could think of it as to forget about the households and just think of the population itself as consisting of x values. 14% are 1, 17.5% are 2. So you don't even have to relate it to reality. You can just divorce it from that and just say, oh, these are just numbers. That could be done if you want, but it's always nice to tie it to reality whenever you can, I think. So once you have a model, you can use it to compute values of population characteristics, such as the mean, make inferences about such characteristics. Let's see what's up next as I try to click on this and see if it'll go. Okay, there we are. So now we have a parameter of a population distribution, and the most popular one is the mean. So we'll kind of focus on that, and we'll look at probability of x, and we'll see how they're going to explain this now. So we found about before in example 3.9, P of 0 was 0.8, P of 1 was 0.2, and 20% of all purchases selected the desktop. Okay, so at another store, it may be different. Maybe it's up to 90% laptops and only 10% desktops. That could easily happen. And it's a Bernoulli RV, and it's represented in the form of P of 1 is equal to some probability called alpha. You certainly will be seeing a lot of Greek letters in a statistics class. It just has lots of it. As I may have already mentioned, when I was very young, I wasn't even 10 years old, I was taking a Greek class. So to me, Greek letters are no big deal. Capital Greek letters look very much like our letters, although there are several major exceptions, such as sigma. But when it comes to the lowercase letters, nearly all of them look different. Okay, so we have alpha and 1 minus alpha. P of 1 they chose as alpha. P of 0 is simply 1 minus alpha because the total must add up to 1. And yes, alpha is between 0 and 1. We don't want them to zero out. So we don't have it all 100% being one value. That wouldn't be any fun at all. So here's the list. We can say that if x equals 0, you have 1 minus alpha. If x equals 1, you've got the alpha and 0 otherwise. I might have started with the alpha first and gone to 1 minus alpha second and just skipped that third line, but that's just me. Your book has a little bit of a different way of looking at things, which is fine. P of x depends on a quantity that can be assigned to any one of the number of possible values, each value having a different probability distribution, and that quantity is called a parameter, such as the mean, standard deviation, things like that. So alpha, a kind of a fixed probability, is a parameter. And every different number alpha between 0 and 1 determines a different number of the Bernoulli family of distributions. So let's take a look at this example. Starting at a fixed time, we observe the gender of each newborn child at a certain hospital until a boy is born. Now this one does get to be a little bit involved, so I'm going to just talk a little bit about it. I think they expand upon this later, so we can certainly handle this one right now. Starting at a fixed time, we observe the gender, and we just talked about that. So little p is equal to P of B, or B is boy. They finally used the first letter of the word. Thank goodness. G is girl, B is boy. So if we get it on the first try, we're just looking at P of B, which is the essential P, which, by the way, they will say is often just considered to be 0.51. It's a well-known fact that there are slightly more boys born than girls. Sometimes they dumb it down, call it 50-50, and in elementary books that happens, but in reality it's more like 51%. So we'd start with that. The first person would just be a boy, and there it is. But what about if it's on the second child, and you have to have a girl first? Then you would have to multiply the girl times the boy, 49% times 51%, a little bit different than 1/4, for example, near 25%, but not quite. So they put in the fact that the girl has a 1 minus p chance and the boy has a p chance. And I might go ahead and add that later on they will just call 1 minus p q. Q is a lot easier way to say it, but right now it doesn't fit the algebra mode, so they're not going to do that quite yet. Now if you do on the third one, they get the boy on the third child. So say you, for example, you have to have a boy. Another way of looking at this is you have enough kids until you finally have a boy. That could be a lot of kids if you have a bunch of girls, or it just might be the first kid. So it'd be a kind of bizarre way to go. But on the third, you'd have to have a GGB situation. In other words, 2 girls followed by a boy. In other words, 1 minus p squared, or perhaps 0.49 squared times 0.51 if you're using the major example. But we can then continue this for probability of x. So notice how if we had to have on the third draw, the exponent was 2. If we had to have it on the second child, I should say, the exponent is 1. So we have a link between x and x minus 1 for the exponent on the 1 minus p. Now I probably would have started with the p. It just looks a little bit easier. Why put 2 binomials back to back? But that's, I don't know, that's just me. Of course, x has to be at least 1. And anything else doesn't make sense, so they just zero it out. And often that statement is kind of skipped, implied to be obvious, but your book is not assuming that anything's obvious. But they do say that p can, of course, be between 0 and 1, and it most likely would be 0.51. It is also known as the family of geometric distributions. They will refer back to that again. Might be appropriate, but if we're looking for the first child with Rh positive blood, not necessarily O positive, but any positive, A or B or AB or O, anything with positive, that turns out to be an 85% chance. So that would change things quite a bit. So it's nice to have a general formula in case you're looking for not girls versus boys, but like event A versus event B, event positive blood versus event negative blood, that sort of thing. So let's go to the next page and keep an eye on the time. Cumulative distribution function. So this one just expands it out and takes a look at what's happened so far. There are actually a lot of reasons for this. And for some fixed value x, we often wish to compute the probability that an observed value of big X will be at most a certain number called x, little x. So the number of beds occupied, that seems a little silly to say that, in a hospital's emergency room at any certain time of day. Suppose we have a table which does let x range from 0 to 4 with various probabilities to go with it. It looks like the number of beds occupied, the most popular one is 2 with a 30% chance. But then the probability that at most 2 beds are occupied would be x being less than or equal to 2, 2 being the maximum. You'd have to add up the 0 probability and the 1 and the 2 all together. It's an easy matter to add these first 3 numbers together to get 0.75. But they like to throw in all these little exceptions, and so if x was less than 2.7, which in the discrete world doesn't make a whole lot of sense, 3 wouldn't be in there. So we just go back to what we just did and just call it x less than or equal to 2, and we'd have exactly the same number. And in fact, if you want to say 2.999, which is not quite 3, which means the 3 is still not included, you'd still have the same 75% number. And then we have other weird exceptions. I may as well just throw them in here. If x was less than minus 1.5, which is, of course, impossible, you would have the fact that you have a probability of 0, which is the same word as impossible. When probability is 0, it's impossible. When probability is 1, it is certain. Those are mathematical words, impossible and certain, and everything else is in between, which is more likely, by the way. X being less than or equal to minus 10, that's also impossible. Any negative number x to be less than a negative number is 0, impossible. And if 4 is the largest possible value of x, for us to say that we're going to be having 4 as a maximum, that's everything. Add it up, you better get a 1. Occasionally you may get round-off error, but by definition, if you got all the cells added together, even if round-off error is going in a slightly different direction, you'll just call it 1. And if x is less than 9.8, that's way out of bounds. It's way over here somewhere. That's still going to be a certain situation, etc., etc., etc. Now, very importantly, if x is definitely less than 2, then we cannot include the 2. So we don't. We just include the first 2 values, and 2 is barely excluded. So it's very subtle, but you have to watch out for your less than or equal to versus strictly less than signs. So that's going to be only 45%, way less than 75%, which is what we just talked about. Okay, and so x is less than x will be less than x less than or equal to x whenever x is a possible value. In other words, a non-zero possibility. If it were allowed to be 0, then they could actually be possibly equal, but that's not going to happen. And so for any number x, yes, you could say that x is less than or equal to its value of x. Cumulative distribution function can be written in a mathematical way, and you can say that f of x, capital F of x, is often used as a cumulative function where it says that x is simply less than or equal to some discrete value x. And there's more notation. You can make sure that y is less than or equal to x and use p of y if you need to. There's just extra notation for you there. Let's work with some of these numbers, basically adding up the columns. These are actually pretty easy. And so a store carries flash drives with either 1 gigabyte all the way up to 16. And so we have the distribution of y equaling the amount of memory in a purchased drive in terms, of course, of gigabytes. And so we have the 1, the 2, all the way to 16 with its various probabilities in blue, which they've just now supplied to you. So we can get the cumulative distribution for each of the possible values of y. In other words, f of 1 is just the beginning number, period. There's not much to tally. It's just the first cell, which is, of course, 5%, also known as p of 1. But now we start moving to get to the 2, and that means you have to get the first 2 cells, cumulatively speaking, starting at the beginning. And then we add p1 plus p2. Once you get the hang of it, it's super simple. 0.05 plus 0.10, 15%, cumulatively speaking at that point. F of 4, you add the first 3 cells to get to 50%. F of 8, get the first 4 cells, that's 90%. And finally, you get to 16. Pretty much by definition, you're at the end of the line. So yeah, you've got the entirety of all that's available, 100%. Now for any other number, you could just slide down to the number that makes some sense. And so equal the value of f at the closest possible value of y to the left of y. So it'll generate a stair-step function, a greatest integer function, which we'll look at in just a second. But if we're going to look at the probability of y being less than or equal to 2.7, then we just go to the 2. And did we do that one already? I think we might have. Yeah, we did. But had different values for that one. But it's the same general principle. So 2.7 becomes a 2 because we don't get to 3 or 4. 4 would be the next number, actually. So we just go to the lower one to the left and use that one instead. 7.999 does not include the 8, so we only have the first 3 cells to tally up, and that is 50% as we showed you back here. And then we have a multi-stepped function here, and they throw the extremes in. The 0 if y is less than 1, not possible, and these are for the cumulative values, and we can talk about some exceptions as well. F of 0.58 is not quite 1, so we don't have any possibility of getting one of them, because that's like f of 0, and if y is at least 16, f of y is greater than 1. So if f of 25 is put in, yeah, it's going to be less than that. It's going to be 100%, even though they don't have one right now that has 25 gigs on it that I know of. So anyway, they throw in the impossible situation. If y is between 1 and 2, including the 1, we're looking at this cell right here, but not quite to the 0.10 at the 2 level. We have the 0.05. We throw in the first 2 cells when y is between 2 and 4, but not including 4. We get, and all these numbers were already added up already. So between 4 and 8, 50%, between 8 and 16, 90% cumulatively speaking. And when you get beyond 16, you've got the whole thing, all 100% of it, known as 1. Here is the stair-step function that we are looking at. However, we now have the kind of the widths often given too, because the y values, that's interesting, they didn't use x, they used y, but that's okay. If you look at values at 1 to almost 2, we have a value which is 5%. So there it is. And also the 0 for anything less than 1, start with that one, and that points off to negative infinity, and there's a 0 probability on that. Not sitting right on the axis it so often is. They elevated it slightly. And then 2 to 4, we see it's about twice as wide as the last one with a probability of 0.15. So as you see, that's just under the 20% mark. And this was even twice as wide as the prior one with a probability of 50%. So it just kind of giving you more. But then By the time you get to the last one, this one goes off to plus infinity. Anything beyond 16 is 100%, so that's known as 1.0. And it's called a step function. It's like a stair step that's not a regular stair step. It starts off slow at first and then starts to jump and then gets extra wide and then it stops. It's a ceiling, so at the end. And the number of births up into and including that of the first boy was also given before, and now we put it into a function that we can use. We actually looked at this already, but x is only allowed to be the number of births up into including that of the first boy. It has to be positive integers, 1, 2, 3, 4. There actually is no limit on this, although practically speaking, there would be kind of a limit that would be nearly impossible to get like 50 on these. It would be just hard to believe, but technically speaking is no limit there, so it's kind of an infinite series there. And they're going through a little bit of math here, and they pull the p out. They also transfer it over to y instead of x, so they're going to go ahead and use the variable y. And y will go from 1 to x, so it has to stay less than x. This is getting a little technical here. I'm getting those error messages. And so this part I'm not overly concerned with. In fact, I put an X by this, so you don't really have to be responsible for this. This is just mathematical juggling, and they're using the geometric series, and they're saying that, yeah, you could come up with another function with the greatest integer function given as the bracket around the X. So that's, yeah, they're trying to make sure you have an integer to put into the function, and then through a bunch of algebra, one could figure out that yes, indeed, yes, you could get a function like that. Of course, if x is less than 1, it's impossible. For any practical value, there's a function that you could use that would be found. It could even put in non-integers, provided you pick the greatest integer function, which you've probably seen before, and that also forms a stair-step function. So there it is, the bracket around the x is the largest integer less than or equal to x. In other words, the bracket around the 2.7 is equal to 2, in case you've forgotten this. And, 2.9 would also be equal to 2, but 3.1 would be equal to 3. So it forms kind of a stair step. And to examine at most 5 births, you could then take a look at the 5, a cumulative function, is what we're looking at. And 1 minus 0.49 to the 5th happens to be 1 minus about 3%, around 97%. When you get out to 10, it's virtually 1. To 4 decimal places, it just rounds to 1. And strangely, they decided to cut ahead to the 50. I don't know why they would do that. But anyway, from 1 on up, that's a probability we may have looked at before, and then it jumps up to the 2. Each of these has equal widths, but then it kind of quickly hits kind of a ceiling of sorts, and that is your 97%. So this is apparently not a linear scale. That does look very weird. And then finally hits the 1 as you get closer and closer. But however, these lines would be so close together that they would be virtually back to back. So this looks like a minor mistake they made on their graph. Now, we could go backwards. I don't know how often we would need to use this, but in case you've been given the cumulative situation, we could go back and find individual values. So if somehow you're locked in with only cumulative values, you can do some subtractions to find individual values. So if you need to find P of 3, and all you have are the cumulative function values, you could take the f of 3, which is 0, 1, 2, and 3 all added together for the f of 3, and then you can subtract away its neighbor, which is up to 2 only. Notice 0 and 1 and 2, all those probabilities are in there, and subtract it away, yielding only the one you want, P of 3. So they're kind of going a little bit backwards on this train of thought. I'd prefer to start here and then see, yes, you do wind up with P of 3. So yes, the two back-to-back cumulative functions could be shaving off the 2, 1, 0 from the 3, 2, 1, 0 will yield just the 3, the P of 3 that we're looking for. And other similar things could be done. If you're looking for values from 2 to 4, 2, 3, and 4, you could take f of 4, which has all the numbers from 0 to 4, and then take off the ones you don't want, namely the P of 0, the P of 1 are not needed. They can be subtracted by subtracting off f of 1, the cumulative function f at the 1 value, which is the bottom 2 values. Then you can find out what those are if you wanted. But it's always better just to have the individual values from the table. This is kind of assuming that those table values are not easy to find, and you just have to work with what you have. I've been in situations like that. And then you have to be careful if you want to you know, do other things. If you have x is greater than 2, that would take away the 2. But here, if you want to include the 2, be careful because you can't just take away the 2 here because we want to keep it. This is 2, 3, and 4, so you'd have to say f4 minus f of 1. So this is the prior example. They subtracted away the 1 because they want to keep the 2. But here, we're getting rid of the 2. Notice no equal sign there. Very subtle. I'm sure you're used to it, but we do want to change things as we need to. We have just a few more things before we get an introduction to 5.3. And so they use a little bit of more notation. They're very good on mathematical notation. So they will say f of b minus f of a minus, which is the largest possible x value that is strictly less than a, such as a 2.999 versus a 3, except imagine a whole bunch more 9s. In fact, an infinite sequence of 9s, virtually. So the only possible values are integers. If a and b are integers, is what we're mostly looking at. So this is getting into more subtle notation that we probably won't have much need for. But they also say you can use a minus 1, but I just don't think we're going to have much call for this. So let's go straight to the example. X could be the number of sick days taken by a randomly selected employee of a large company during a particular year. The maximum number of sick days is 14. Possible values are from 0 to 14. And f of 0, which means that they're definitely taking only 0 sick days. This is me. I've gone many years without taking any time off. I just don't get sick. I'm like my dad. He was sick like once a decade. That's kind of me, maybe twice a decade for me. So anyway, this f of 0 is the same thing as just p of 0 because all you have is 0 to look at. Now, f of 1 is the 0 and the 1, so you see it's jumped up to 72% cumulatively. That is at most 1 sick day used. At most 2 sick days used is 76%, and they stopped keeping track at 5. So that's between 0 and 5 sick days used, 94%. Now, if you need to get the numbers between 2 and 5, you could then notice that x could be 2, 3, 4, 5, and then you could subtract just like we did back here in the prior example, f of 5 minus f of 1. And f of 5, 94%, f of 1, 72% yields 22%. And if you needed to find exactly 3, for example, you just take the cumulative function of 3 minus its neighbor, the one at 2, and then you'll get just p of 3 in between at 5%. And okay, and you can do other combinations too. So here I think we're going to have a fields of exercises. I'm going to go ahead and jump into expected values so we can get our foot in the door on 3.3. So my plan would be to finish 3.3 and review for the test on the live lecture coming up on Wednesday, the 24th. Our test, of course, is on Monday, March 1. It'll be the entire class period. It'll be on Blackboard. We'll have more details coming up as I get my test together, which I have not done as of this taping right now. Consider a university. This is expected values, which is kind of like a mean. It basically is a mean. X is the number of courses for which a randomly selected student is registered. The PMF is as follows a table, and P of 1 is 0.01. So somebody taking only one class is right there. And then expanding it out to the 15,000 students, we figure that's going to be 150 students that just have one class. And it ranges all the way up to 7 classes. I've known people that did that. I had a genius friend of mine that took 7 very heavy classes. I just love telling the story. Advanced calculus, advanced physics, electronics, computer science. He was the smartest guy I've ever met. He had 7 finals in one day at Cal Poly Pomona, and he got A's on all 7 finals. They were only 2-hour finals, but still, that's incredible. He came in our math lab. I worked the math lab then. And after his 4th final, he said he was starting to feel a little tired. He had to go well into the evening to finish his 7th final. I found out later he aced them all. Wow. You don't meet people with IQs of 200 very often, but he sticks in my mind. Very smart guy. So it's very humbling to be around people like that. I'm not a person like that, by the way, in case you were wondering. But anyway, we have this table. We can see all the values. Most popular apparently is 5 classes. And the average number of courses, as it'd be like a weighted average, can be found. They show a couple of different ways to do it. They first look at the total number registered that fit all these categories based on the percentages that were given, the proportions that were given. So let's see, the average number of courses per student, you might think is around to 4, and you wouldn't be too far off as you look at the answers, around 4.5. So we could take a look at 150 people taking one course, and then 450 people taking two courses, and get like the grand total number of courses that are taken divided by the 15,000 students. This is certainly a good way to look at it. May not be the easiest way, but it certainly is a good way to do it. And so when you get all those total number of classes together, which they did not tell us, but you divide by 15,000, it's got to be over 60,000. Your answer would be 4.57. But instead, why not use the proportions that they gave us in the first place? So instead of bringing in the 15,000, all number of people, why not just take 1 times 0.01, which is here, they just didn't list it, and 2 times p of 2, 0.03, et cetera, et cetera, et cetera, all the way to get to the 7 at p of 7, 0.02 is back here. And it turns out you get the same answer, and the expressions on the next page will kind of verify that. I'm pretty sure it does. Is that what they do? Actually, they don't actually. Well, yeah, they do. They'll do that on the next slide. So let's take a look at that. And as we get to what they call the expected value of x, we can take a look at the x times p of x's and sum them up for the domain D, I guess. And that's what they've done here. This would have been easier if they just said it in the first place, but they wanted to give you a different alternative look at it. Okay, so 1 times 0.01, 2 times 0.03, on and on and on, and all the various numbers show up here and adds up to 4.57. Yeah, so about 4.57 classes per person is what they got from this particular survey. And the mean is not 4, the ordinary average of 1 through 7, because the distribution puts more weight on 4, 5, and 6 than on the other x values. So can't see the chart from here, but if you recall, or I can turn back a page or so, we had the most common was 5 classes, 39%, and 6 had 17%. So there was more weight towards the end, not towards the beginning. So that's why it got skewed a little bit over to the other side. We have another example. We have just a few more examples to show you here. And so just after birth, we rate newborn children on a scale called the APGAR scale. Ratings are from 0 to 10, and the child's rating is determined by, I guess, skin tone, muscle tone, respiratory effect, et cetera, and the best is a 10. Only 1% of the children get a 10. And not too many, luckily, get a 0. That means you're not doing too well, I guess. I don't know much about this. But we could find out what the expected value of x would be. And we could find out what the average rating would be. 7 happens to be kind of a modal class. It's the most popular one, and not too surprisingly, our average works out to be just higher than 7. So they took the score of 0 times a very rare p of 0, and then 1 is even rarer than that, and it gets multiplied by 1 all the way out to the 10, which is a bit on the rare side too. So you just multiply all those numbers together, add them up, and you get an average score of 7.15. And here's another one. Looks like a Bernoulli random variable. 1, if the selected vehicle passes an emissions test. I just got a smog check a few days ago, and x equals 0 otherwise. And so if p of 1 is equal to p, then p of 0 is equal to 1 minus p, sometimes known as q, but not quite yet. So we could find the expected value of x by taking 0 times its probability plus 1 times its probability, or in terms of what we just labeled it as, 0 could get the 1 minus p, it zeroes it out anyway, and the 1 could keep the p, and that just works out to be a p, which is what we started with. So it's like we're talking in circles. That is, the expected value of x is just the probability that x takes on the value 1. Okay, mu equals p. Amazing. The children born up into, including the first boy, we've looked at this one before. You could call this pq to the x minus 1. But at least they put the p first. And here's where they get into a little bit of calculus, and I don't know if we're going to actually need to do this, but it is a nice coincidence that the geometric series happens to be the derivative, negative derivative of the process of the geometric series. And so for those of you that have had some more calculus, please take a look at that, but I'm not going to hold you responsible for it, but it's just a nice thing they pointed out. Here's another example. The number of interviews is x, and that's the number of interviews a student has before they get a job, and we could have a function along these lines. First interview, you've got k over 1. Second interview, k over 2 squared or 4, but the constant has been determined to be pi squared over 6. That's roughly 1.5 or so. Pi squared is about, 9-ish. So it's over 1.5. Don't worry about that. But this is just a function that they could get. And to get the expected value, we could go ahead and use a summation from x equals 1 to infinity. I hope you don't need to have an infinity number of interviews, an infinite number of interviews. And this gets into a series as well. So they kind of use a little bit of algebra and find that you got k times 1 over x, the sum of the 1 over x's, which turns into a harmonic series. That's actually interesting because the harmonic series is actually pretty simple. It's just the 1 over x's. But this tends to grow without bounds. They have a little bit of math talk here where it has a heavy tail. They kind of lose the battle. It just doesn't decrease fast enough. So it turns out we have, and I guess L'Hopital's rule might be used on this, in fact, but heavy tails in connection with some distributions mean that we do not have typical inferences about mu. This would not be easy to do, that's for sure. Okay, looking pretty good time-wise, so I think we're going to get to a stopping point here. My plan is to try to finish 3.3 before we do a review on the upcoming Wednesday. So work on the WebAssign. I've already opened up 3.1. I'll be opening up 3.2 very soon, and 3.3 as well. So I'll get those ready for you very soon. Can't say exactly what day, but it won't take me too long to get to that level. All right, so study hard, and we'll see you in the office hours on Wednesday. I'll definitely see you live on Wednesday. This is for the Monday lecture 222, covering sections 3.2 and the end of the beginning of 3.3. So take care, and we'll see you soon. Bye-bye.